And now I'll go through a very popular op-amp configuration, and that's the inverting amplifier. In the inverting amplifier, you will see a source connected through a resistor, and both of them will be connected to the inverting input. And then there's a feedback loop from the output going back through a resistor and going back to the inverting input as well. So my goal now is to see how does V out relate to V in, and specifically the ratio between them, which we typically call the closed loop gain. The closed loop because there's now a loop, a feedback loop, a negative feedback loop, that is. All right, so let me just get started in here. So the first thing I'm going to do is I'm going to apply my assumptions. The assumption is the negative current, or the current going into the inverting input, is 0. And also the current going into the positive input is 0, and of course, because the open loop gain, what we called A, creates what we call a virtual short in here, and in virtual short, I know that VP is 0 because it's connected to ground. That means also Vn is 0. So let me just write these here. So what we have is we have the In is equal to Ip is equal to 0, and we have Vp happen to be 0. That means Vn is also 0. And now what I will do next is I'll say, well, here's node 1, here's another node in here, and here's another node 3. And what I need to do is I need to apply nodal analysis. And there's multiple places where you can apply nodal analysis. For this particular configuration, it would not make any sense to apply it at 2, because I know that the current's going like this way and this way is 0. So, and actually I know what the voltage at 2 is. And also at 3, generally speaking, it's a little bit more difficult to apply it at 3. And the reason why is because the current coming from inside of the op-amp is unknown, and we can't write, I can't just write V out minus, I don't know what's inside it. Okay, and so I don't know this current and I don't know the voltage in here. So typically we'll avoid writing nodal at the output. So yes, the input currents are 0, but the output is not 0. You might be wondering, where is the current coming from? Remember, there are power supplies that are connected to these to this op-amp. So these power supplies do provide current. That's where the current is coming from. So that leaves us with this particular node. So for this particular node, I will write the nodal analysis. For this particular configuration, it will make sense to write them here. So let's get started. So I'll say, well, the first one is Vn for the negative minus V input divided by R1 plus, I believe it's Vn minus V naught divided by R2. And that's basically nodal analysis. So we have, I assume that there's a current in here, that's this one, and then the other current is the current going that way, which is basically this V minus this V, which is V output divided by R2. And of course, I don't need to write plus 0 because that's just a 0. So we just say this is 0. We'll clean. What we do is as well is we know that Vn is here is just simply 0. So this is 0. So all I have to do is just do a little bit of algebra, and you'll end up with this equation, which is negative Vi divided by R1 equals V out divided by R2. And if you move the algebra a little bit or move the terms a little bit, you'll end up with V naught is just simply negative R2 divided by R1 over Vi. So this here is the relationship between the output to the input. And if you take a look at it, it all depends on the values of R2 and R1. So if I really take the ratio between the output to the input, I'll get what we call the gain, okay, and specifically the closed loop gain, and usually we call it G, closed loop gain. So if you take a look at this now, what I've came up with now is these are external resistors. R2 and R1 are external to the op-amp, and I was able to get it into a configuration that will amplify the input by the ratio of R2 and R1. Actually, it depends on the values of R1 and R2. Amplification could be in the positive. Amplification make it bigger or smaller. If R2 is smaller than R1, the signal at the output will be smaller than the signal at the input, and vice versa. If R2 is greater, that means the signal at the output will be greater than the signal at the input. So that's pretty much the inverting amplifier. So what I will do is now I'll solve an exercise using this particular equation. So let me just do this here. Let's solve it. It's very quick, just so that to show you the effect of using it. So here's that inverting amplifier, and what I have done in here is I just gave myself a few values, and this is basically 100 kilo ohms for the R2 and 1 kilo ohms for the 1, and I told you, well, the input is 0.1. Let's take a look at the V naught here. So the V naught, based on these equations, of course you can write nodal analysis, but if you detect one of the configuration, there's multiple configuration for op amps, you can just use the equation if you already know it. So I already know this here, so simply V naught will be negative R2, which is 100K divided by 1K, times the V input, which is 0.1, and you'll see that's simply negative, I believe it's negative 10 volts. Okay, so now this is the reason why we call it an inverting amplifier, because we had a positive voltage as the input, and what we got is we got a negative voltage at the output. So we have here, we have now negative 10 volts in here, so it actually inverted the sign of the input. And the other thing that you see in here is now we had an input of 0.1 volt and we got it expanded to 10 volts, and that's one of the usages of the inverting amplifier. Now, before I move on to different configuration, what I want to do is I want to just reiterate the assumptions that I've done. So the assumption told me, and I'll replace this with a model. Let me just do this here. So this is the same circuit with the same examples, same values. So what I've done is the assumptions is there's no output, there's no input resistance. We said that this input resistance in here, the Rn is just tends to infinity, and also we said that the R output tends to 0. But what I will do is I'll just basically say, let's assume that A did not go to infinity. So I will say A did not go to infinity. So if that's the case, and A, if you guys remember, it's just the open loop gain. The open loop meaning there was no loop in the backwards. So this is just internal here. So let's see the effect of having A not to be infinity. And in that particular case, if A is not infinity, that means I don't have a virtual short between here and here. So the VP is not necessarily equal to Vn. So I know what VP is, which is 0, but I don't know what Vn is. So I'll have to write a nodal analysis. And I'll write nodal analysis at 1 in here. Okay, and that's a 2, and that's a 3. All right, so first, I want to see what V naught is. Well, V naught, based on this particular model in here, is just simply A times VD, but we know what VD is, and that basically is VP minus Vn. But we know what VP is. VP is just simply 0, so I'll say V out is just simply negative A Vn. That's basically in here. And again, I don't know that Vn is 0 because there's no virtual short, because A is not infinity. Okay, so now let's write a nodal analysis here, or nodal equation in here. Okay, so that tells me that Vn minus 0.1 divided by 1 kilo ohm plus Vn minus V out divided by 100 kilo ohms, and that is equal to 0. All right, so now what I will do is I know what V naught is, so I'll just basically substitute it in here. That's all. So I'll substitute this value in here. So that will tell me Vn minus 0.1. And actually, let me just do a little bit here. So I'll multiply both sides with 100, just make things a little bit easier for me. Vn minus 10 plus Vn minus V naught equals 0. And then I will say, well, I have 101 Vn minus V naught equals 10. Okay, and now I'll substitute this here instead of the V naught. Okay. All right, so we do that, and that's 101 Vn minus times minus, so it becomes A Vn equals 10. Okay, and that's basically 101 plus A times Vn equals 10. All right, that means that the Vn is simply 10 divided by 101 plus A. But what we're interested in is typically the output, not the input. So I'll just basically go back in here and substitute it. I know what V out in terms of V in is, and that's just simply negative A times 10 divided by 101 plus A. Okay, so of course, if you take a look at if you basically make A equals infinity, it will see, well, let's do this. If A was infinity, as we have done before, you will see that this term and this terms grow much larger, very bigger together, with regardless of the 101. So what we would do is, just simply this will grow and this will grow bigger, so I'll end up with, like, if A tends to infinity, that means the V naught will tend to be equal negative A times 10 divided by A, and of course A goes with the A, so that's negative 10 volts, and that's what we've seen a few minutes ago. But anyway, if A was not infinity, and I gave myself a few examples in here, or a few values, so what happens, like if A happened to be 1,000, and you just substitute 1,000 in here, 1,000 and so forth, what you will see is the gain now, instead of negative 10, I'll get negative 9.083. If A was 10,000, you will see that it becomes negative 9.9, and the larger it gets, the closer we are to the negative 10. And that's the effect of having A not be extremely large. Typically speaking, in practical applications, or we just assume that A is infinity in ideal cases, and in practical application you'll see it's pretty large. It's, I think in the data sheet we've seen in a previous video, was about 200,000, so it's very, very close to the infinity.